decimal arithmetics. So we'll start from the introduction of the definition of decimals, and then we'll extend this to the addition, subtraction, multiplication, division of decimals, so the arithmetics between decimals. So in the past, we have already learned how to represent the non-integers as fractions, right? We first start with integers, and then we find out that during the integer divisions, some of the numbers are divisible, but some of the numbers are not divisible. And for those not divisible numbers, we can still keep them in a fraction form, right? So further extended from the fraction form, we are also able to write the fractions into decimals. And in fact, integer numbers are also a special case of decimal. So in this chapter, we will start to learn a different way to express the numbers or the fractions, which is decimal. So it all starts from our base 10 number system. For example, when we write out a number with several digits, the digits means power of tens. Right, so for example, if I'm just write a random 3-digit number 572, the reason I'm able to write this in this way, because I want to express, I have a quantity which is taking the sum of 5 hundreds and 7 tens and 2 ones, right? So then I'm able to write the third digit as 5, the second digit, the 10th digit as 7, and then the 1st digit as 2. This is all because of the base 10 system we have. Basically, when the single digit 1, 2, 3, 4 accumulated until 10, we move to the next digit. So the base 10 digit can be further simplified with a single number as the digit number, single number multiplying by power of tens. For example, the 100 digit is a single number times 100, or 10 squared, right? 100 is second power of 10, so 10 squared. And then the 10th digit is a single number 7 multiplying by 10 with power of 1. And then the last digit, the 1st digit, can be also written as power of 10, but just this case, the power is 0. Recall that what we learned from exponents, that power of 0 means is equal to 1. All right, so then that's how we say that this 5 is on the 100 digit, and then 7 is the 10th digit, and 2 is the 1st digit. Right, so this is the integer, right? This is what we have learned. We have been seeing this all over in many different places. Now, intuitively speaking, digit by digit, the power of 10 increase 1 by 1. So intuitively, you can think about what happened to the other side. Like, what happened if I keep decreasing the power from 0 to -1 to -2? So that's the concept. Help us to extend from integer to decimal number, from integers to decimals. Like for example, if I have 5 times 10 to the power of 0, so that will be the 1st digit. And then if I have 7 times 10 to the power of -1, then 2 with 10 to the power of minus 2. Right, then we have 5 plus 0.7 plus 0.02. You will learn that with more practice at a later time, but I'm just writing this quickly to show you that this is the same way that you can expand a decimal number into power of tens. So the decimal is still within the base 10 system, it's still part of the base 10 system. It's just it's a extended way to show more options of the power of tens, so that you can also express your decimal numbers in this way. And here we call, for example, we already know that we call this is the ones digits. Now the number 7 here, because it's times 10 to the with the power of minus 1, so it's equivalent to become multiplying 1 over 10, right? And this is equivalent to become multiplying 1 over 100, right? That's what you learn in the exponents. So as a result, we also call this digit, the one digit after the decimal point, is the 10th digit, because that's the number that you divided by 10 or multiplying by 1 over 10. And then this is the 100th digit. The 100th digit, right? 1 over 10, 1 over 100. Okay, so this is how we express a number in a decimal form, where the definitions or each components from a decimal number. So now we can see a extended example with two decimals added together. For example, and in this example, we will start by its definition. So for example, if I have 2.6 plus 3.1, what is the value of these two decimal numbers added together? You probably already be able to tell the results, but let's start from the very beginning, from the most basic definition or the concept of the decimal number, to show you step by step on how to do the addition. And after you seeing this, you will know that what is the usual way that we're doing the decimal addition, and why we can do that way. So first, a decimal number under a base 10 system can be further written as 2 plus 0.6, right? I'm trying to write each digit apart. The second number is 3, which is a 1st digit, plus 0.1. 1 is the 10th digit, right? So in other way, by writing out its digit clearly in the base 10 system, number 2 should be written as 2 times 10 with the power of 0. This is 6 times 10 with the power of minus 1. 3 with 10 to the power of 0. 1 with 10 to the power of negative 1. Now we can taking out those numbers out from the brackets and group the similar terms, basically group the terms with similar multiplier or similar factor. So have two numbers are having a factor of 10 to the power of 0. I have two other terms with a factor of 10 to the power of minus 1. So I write them together by regrouping them, because addition is commutative, right? And this brackets doesn't change anything, doesn't have anything to do with the calculation. It's just to show it in a more clear way that you will see that we're going to, which terms we are going to group. So then we're going to group the first two terms. The common factor is 10 to the power 0. I have 2 plus 3. Similarly, common factor, and I have 6 plus 1. So I have 5 times 10 to power of 0 plus 7 times 10 to power of minus 1. And then there's no other numbers that having the same base. So all the numbers are grouped together with the same base, either base 1 or base 1/10. So then this is how we write the decimal number 5.7. Okay, so this shows the addition of 2.6 and 3.1 is 5.7, and this is derived right from the most basic definition of decimal numbers. And of course, in practice, when you do the addition, you probably see that you do this very similar to what you did for integers as the long addition, for example. We'll see more examples. It's not that as easy as you think about. There's a little bit tricky. In some cases, we'll see that soon. Now let's see the second example. How about 13.9 plus 2.37? Again, when we do the addition, if we do addition around integers, for example, 23 plus 6, then we can do the long division in this way, and adding the number from the same digits together. This is an imaginary 0, so 2 plus 0 is 2, right? This is how we do this for integers. And we have the other example that how we do it for some cases for decimals. Now, what can you tell from here why we're doing this way, why we're not doing this way, right? Because number 2 and number 6 are not coming from the same digit. And furthermore, as I said earlier, integer is also a special case of decimal. It's just all the digits after the decimal points are zeros. So you can also imagine that this is 23.0 plus 6.0. So in this way, we're not just aligning the last digit, we're in fact aligning the decimal points when we do the long addition. Now you see the difference. If I'm doing this addition, I have 13.9, I have 2.37. If I'm writing in this way, 2.37, I'm actually adding them with the wrong digits, with the mismatched location. So I need to match the decimal point. If the decimal point is here and here, then the second number is 2.37. So you see that 7 is actually the third digit after decimal, and the 3 and 9 are the first digit after the decimal, right? Or in some case, if it's not that easy for you, you can add a imaginary 0 after the decimal. You can always, for decimal numbers, you can 2.3, for example, you can add as many as imaginary 0 after the digits that after the decimal point. You cannot add for integer. So for integer, you cannot do this way, right? But you can add as many as zeros to the left. That's the same thing. So anyway, so back to this example. So you want to align the decimal point so that you can making sure, or sometimes if necessary, adding some imaginary zeros. So this will tell you which digit exactly you want to do the addition or subtraction or whatever calculation. So here, 0 plus 7 is 7, 9 plus 3 is 12, so I got 1 here, round it to the next digit, and then this 5 is 6, 1 plus 0 is 1, and don't forget the decimal point. So this is really equals 16.27. And that's how you solve the decimal addition for a relatively complicated case. And similarly, we can see another example with subtraction. Now, this time we have 0.135 minus 0.28. We actually have a smaller number subtracting a bigger number. Usually I would prefer to always, if I need to write the long subtraction, I would always prefer to write the bigger number to the left and the smaller number to the right. So this is equivalent to having the minus sign in the front, and then I can exchange the order by having a larger number subtracting a smaller number. And then I can use the long subtraction form here, making sure the dots, the decimal point, is in line between the two numbers. Then 135. This time I'm doing the subtraction, and again, if it helps, then you can add the imaginary 0 to help you do the calculation. Then I have 0 minus 5. It's not sufficient, so I need to borrow one digit. So 10 minus 5 is 5. 8 becomes 7. 7 minus 3 is 4. 2 minus 1 is 1. So this is 0.145. And then don't forget the negative sign that we added in the front, so it's negative 0.145. Okay, so this is how we do the subtraction. Okay, so then we had some practice for addition and subtraction. So the next step is to see how we do the multiplication divisions. So first, multiplications. If I have a decimal number 2.59, and I'm just multiplying this by 100, so this would be a very simple example. But again, this is the first time we see an example with multiplication. We'll also want to try to solve it right from its definition, like that one. So let's try it. You probably should be more familiar now. So if I'm quickly writing out the first decimal number by separating each digit with the corresponding location in the base 10 number system, I can write my decimal number into 2 times the 1st digit plus 5 times the 10th digit, and then 9 times the 100th digit. Multiplied by 100 is 10 to the power of 2. Now this is just the redistribution of multiplication. I'm distributing this 10 squared to each term. And then I'm having exponents with the same base. That's what we learned from the exponent, that if you have the same base, then the power is addition. So 0 plus 2 is 2. This is minus 1 plus 2 is 1. Minus 2 plus 2 is 0. Okay, then we have every single number associated with a different base 10 location, or 10 with a different powers. Then we're at the second last step. Then we can write it back to the decimal form. So this is 100 place now. And this is 10 place, not tens, 10 place, and this is 1 place. So then your result is 259. Okay, so this is how you do the multiplication from the definition. And you can also tell that if I'm multiplying a decimal number with tens or hundreds with any number as 10 to the nth power, you do not change the numbers in each digit. You're changing the decimal point, right? 259 equivalent to 259.0, right? So you're actually moving the dot without changing any other numbers. So what we can concluding from here is that multiplying by 10 to the nth power, basically any base 10 or any power of 10, means moving each digit n positions to the left. Of course, here n is greater than 0. For example, 10 squared, 10 cubed, 10 to the positive number of powers. For example, to 10 squared, right? Moving the positions kind of leftward. Now, similarly, this also equivalent moving to the right if n is less than 0. So, for example, if you are multiplying 10 to the power of -3, it means you're moving to the other side. So this helps you to quickly moving around your decimal number with multiplying multiple of tens. And why we need that, we'll see that later, because this will help us in a very quick way to simplify or to convert our decimal number into a rounded number, which are integers, and this will be helpful in the decimal multiplications and divisions. And let's see two quick examples before we move into that. Just want you to see more examples to get more familiar with moving the digits. Intuitively speaking, if I'm dividing some large number, then my number should become smaller. So this also helps you to determine or memorizing how, like whether the digits should be moving to the left or the dot should be moving to the left or right. So usually I'm dividing a large number means this number should be getting smaller, then the dot should move to the left. And then I have 3 zeros, that's well, dividing equivalent to dividing 10 to the power of 3, and then this equivalent to multiplying 10 to -3. So we are in the second case. So 10 to power of -3 means moving 3 steps to its digits, right? So moving all the digits to the right equivalent to moving your dot to the left. So moving 3 digits, 1, 2, and 3. See here we probably need a couple imaginary zeros to help us locate the right digit. So then the results would be 0 point, right? I'm moving the dot over here. So I have a 0 in front, I have a 0 after, and then it's 3, 6, 7. Okay, so you need to be clear how many digits you're moving or how many steps your dot is moving. And if there are not sufficient digits, use the imaginary zeros to help you. Another example, if I have 0.0028 multiplying by 1000, first of all, 1000 is 10 to power of 3. This means I'm moving my decimal point 3 steps, and to left or to right, I'm multiplying a large number, so this number should clearly be greater than the original number. So which means I'm moving the dot to the right. I'm moving the digits to left, or equivalent to moving the decimal point to the right, and by 3 steps. So 1, 2, 3. So it's over here. That means my result is 2.8. Okay, so now you can see that we actually have a efficient way to convert the decimal numbers into an integer by multiplying power of tens, right? Given a random decimal number 0.23, if I want to convert this into an integer, this means I'm multiplying 100, dividing 100, and this number multiplying 100 means you are moving the decimal point 2 steps, so you get 23. So it's 23 over 100. So even though it's still a fraction number, it's not a real integer number, but I'm replacing the decimal number into a couple of the integer numbers. And later on, the integer number will help you to do the multiplication and division. So that means for every decimal number, you can first convert this into integers by multiplying a power of 10. Here the power can be positive, can be negative, but it's always a power of 10. So then your decimal will then first be converted into integers, and then this can be used in the multiplication and divisions. So for example, 2.9 multiply 1.3. So to solve this one, I can first rewrite each decimal to integers. For example, 2.9 is 29 times 10 to the power of minus 1, right? Because 2.9 is 2.9 multiplying by 10 divided by 10, and then 2.9 multiplied times 10 is 29 divided by 10, and then divided by 10 means 10 to the power of negative 1. But you have many different ways to convert this, so this is just show you that 2.9 can be written as 29 times 10 to the power of negative 1. Similarly, 1.3 is 13 times 10 to negative 1. And then everything in the inside or outside brackets are multiplications, so which means I can take off the brackets as is and have 29 times 13 times another 10 to minus 1. And then I can multiplying the integers first and then group the rest of the power of tens together, right? So which means I still need to do the calculation to find out what is 29 times 13, but the other two terms are 10 to power of minus 2, right? That's the property from exponents that if you have the same base, the power are add up by additions. And then if I know 29 times 13 is 377, I have 377, the multiplication of 10 to power of negative 2. And then eventually write this back to decimal. This time it's negative 2, and the integer 377 means you are 377.0. So then moving this decimal point 2 digits or 2 places, 1, 2, means that your final answer is equivalent to 3.77. Right, so this is how you do the multiplication by converting the number into integers first. Converting your number into integer, multiplying with a power of 10. We can do the same thing for division. If I have 0.48 divided by 0.6, it can first be written as 48 times 10 to the power of minus 2 divided by 6 times 10 to power of minus 1. This time be careful because it's dividing, right? So that means it's divided by 6 and divided by 10 to minus 1. So I can group the non-tens number together and then put the rest of the power of tens in another place and divide it by 10 to minus 1 equivalent to multiplying 10 to power of 1. Okay, so then 48 divided by 6 is 8. And these two combining together, it's under the same base. So it's minus 2 plus 1, so it's minus 1. So it's 8 times 10 to the power of minus 1. And it's essentially just 0.8. Okay, now we can use another way to verify these results. And another way that for decimal divisions, so this give you option 2, 0.48 divided by 0.6, right? You can also write this in a fractional form first, and then to convert the decimal numbers within this fraction, it's equivalent to multiplying, first observing that I have 1 digit here and 2 digits here. In order to completely removing decimal point, I need to multiply at least 100 to remove the decimal or to move the decimal point to the end. So that is equivalent to multiplying 100 on both sides of this fraction, right? So then it is still equivalent. Then it's equal to, this becomes 48. This, be careful that you're moving 2 steps, so it's 60. Right, so this is another way to convert the decimal division into integer divisions. Then here will be the same thing. You can either do the simplification or do the long division directly. But here, if you like, you actually have at least have a factor of 2, give you, sorry, factor of 4 give you 12 over 15. Then a further factor of 3 give you 4 over 5. And then 4 over 5, 0.8. So you'll get the same answer from here. Okay, one more example to check the division of decimals. So we could have another kind of question asking that if I have 0.0481 times 10 to power of minus 4 equals 4.81 times number of n, then what is the value of n? So this one, you actually don't need a calculation. You can first observing the difference between the two sides of the equation. I have one number over here and another number over here, and I see that all the digits are having the same value. It's just the decimal point is at a different location. And if I'm moving this decimal point 2 steps to the right, I will get the 4.81 as well. So this means this number is 100 times smaller than that one, right? And then 100 times smaller, multiplying 10 to the power of minus 4 will get you the value of n. But let's do this step by step. The other way, I think the easier way is to convert both numbers into integers. So in that way, my left-hand side, if I want to convert this to be an integer of 481, that means I need to keep moving my decimal point. So 1, 2, 3, 4. Right, 4 steps. So this means I need to multiply a 10 to minus 4 to get this number still equivalent to the original number. And then don't forget you have another minus 10 to the power of negative 4. And then similar to this side, if I want to write this as an integer of 481, I need to move my decimal 1, 2 steps. And this means I need to multiply 10 to power of negative 2 times n. So then I don't need to tell more, but I can just directly cancel out the same number 481 from both sides, and the rest of the number is 10 to minus 8 equal to 10 to minus 2 times n. If I'm multiplying the 10 squared on both sides of the equation, I get this plus 2 is 10 minus 2 plus 2 times n. And this is just 1. So here my n is 10 to the power of negative 6. And this is how I solve this unknown variable n. Okay, so after seeing the arithmetics such as additions, multiplications, and divisions, we will review the last important concept from this class, which is rounding. So rounding is a very important concept that you will use it later in, for example, physics, engineering, in many places that you have a very long decimal, but you only want to know the approximated value. You don't really need such many digits. Then you would use the technique called rounding. Okay, so the rounding will help you to simplify your decimal number. And there's a certain logic or certain rules when you do the rounding. So we start from rounding the integer first. And later on you will see that rounding integer and rounding decimal is the same thing. So if we want to round an integer to a particular power of 10, again, because we're all within the base 10 system, so we're rounding to a certain power of 10. For example, rounding to hundreds, for example, it's a power of 10. This means to find the closest number, that is a multiple of the chosen power of 10. Like, for example, if we chose power of 2, then that's the chosen power of 10. And intuitively speaking, for example, if we want to round number 31 to 10th digit, then 31 will be round to 30. That is very clear because the closest number with power of 10s around 31 is either 30 or 40, right? And then 30 is closer than 40, so 31 will be rounded to 30. Or if the given number is 39, the two neighboring power of 10, chosen power of 10, still 30 and 40, but to the number of 39, 40 is closer to 39, so 39 will be rounded to 40. Now you will see that 31 or 39 is just too obvious. What happens if you are right on the midpoint? Right, I can understand that 31, 32, 33, 34 are clearly closer to 30, or 39, 38, 37, 36 are clearly closer to 40. But what happened to the midpoint? So there is a special way or special rule. So if a number is exactly halfway between the two, let's call them whole multiples, like hundreds or tens or hundreds or thousands, we'll pick the larger one. Right, so we just simply pick the larger one. So 35 has the same distance between 30 and 40. Then we pick the larger one, we pick the 40. Okay, let's take another example. Let's say 13,000 rounds to 1,000 digits. Right, 1,300 or 1,300s. Rounding to 1,000 digits, the two neighboring 1,000 digits are between 1,000 and 2,000, right? And then 3 or 13 obviously closer to 10 hundreds or 1,000. So this number rounds to 1,000. And then for 1,500, it's still between the two rounded number of two whole number, 1,000, 2,000, and it sits in the midway. It's the same distance between the two neighbors, and then we pick the larger one. So 1,500 rounds to 2,000. So that's simply just the rule. Let's extend this to an example that contains both integers and decimals. So, for example, if I have a number 697, I want this round to the nearest hundreds. Okay, so the hundreds number between or surrounding this number would be 600, between 600 to 700, right? And then 9, checking the next decimal, 9 is clearly greater than 5 or greater than 4. So then we need to round up because 9 is greater than 4. So round up to 700, right? If I have 647, because number 4, it's smaller than or equal to 4. So this will be round down to 600. Right? I don't even need to care about the third digit. I only need to care the one digit that after the rounding digits. If I want to round to 100, I only need to care about the 10th digit. So similarly, if I have a decimal number and I want to round this to the nearest 10th. Okay, so where is the 10th digit? It's over here, 6. So I'm still need to care about the digit that right behind the digit that I want to round. So then this digit is 5, which is greater than 4. That means I need to round up. And the tens digits around surrounding this number is 1.6 to 1.7, right? So then by rounding up, this number will round to 1.7. Okay, so this is how you round down and round up. Now, the tricky part or the special case is for a negative number. See that we always say that you need to round to the larger one. So when you have a negative number, for example, negative 2.34, and you want to round to tens decimal here. Now, even though number 4 is smaller than or equal to 4, to the other examples, you seems need to be rounded down. But it's a negative number. So it's round down means round up increase. So this is in fact between minus 2.4 to minus 2.3. So the larger number here would be, let's use 5 for example first. So it's 2.35. So then we can see that when we say round up in this case, right, because we're at the midpoint 5 and we want to round up, so then it's really round up to the larger number in this case, which is minus 2.3. So it rounds to minus 2.3. Instead, if it's a positive number 2.35, right, I don't need to write all the details, but you can perhaps now tell it quickly. This, if it's a positive number, then it will, because of the number of 5, it will be rounded up to 2.4. It's not 2.3. So be careful for the negative number. The larger number is the number that is smaller without a negative sign. So that's all for this part of the class.